High energy experiments right now is a pretty exciting field. There are a number of big questions that we're trying to answer. These range from, where do neutrino masses come from? What is dark matter? Where does the Higgs really come from? What's the origin of the Higgs and the Higgs mechanism? Why does it have the mass that it has? And these are all questions that, we have experiments right now that are operating, that are being constructed, that will, provide input on those kind of questions. And so at the University of Minnesota, for example, we have a pretty active high-energy experimental group. We have people working, such as myself and a few other colleagues, experiments at the Large Hadron Collider, where we have, collider physics, but we also have an active group in neutrino physics, dark matter experiments, even cosmology. So, and the strengths of Minnesota in terms of high-energy physics, I would say on the collider side, we have a really strong group in calorimetry and on detector electronics. So these are the electronics that live really on the detector. They have to be exposed to radiation. They have to be able to operate stably for, let's say, you put it on 20 years and it still has to work. And so we have a lot of expertise in that. On the neutrino side, we have experts in liquid argon technology, which is something that's sort of an up-and-coming technology that will be used for the foreseeable future in neutrino physics. So
there are two of the biggest questions in physics that the field is trying to sort out. One of them is how the universe began, and the other one is what is the universe made of. And so as far as how the universe began, we're trying to figure out what happened right after the Big Bang, 10 to the minus 35 seconds after the Big Bang. Measurements of the cosmic microwave background can tell us what happened right then and there. In terms of what the universe is made of, as you know, and many other people know, we know that the neutrinos have mass, but we don't know what is the mass of the neutrinos. And cosmology and cosmic microwave background would provide key measurements to determine the neutrino mass in the next few years.
One of the big questions in the field that's been there for, more than 40 years is, what do strongly interacting quantum field theories do?
So, starting with what we do at CERN, things which we do there range all the way from designing bits and pieces of electronics, data analysis in a very detailed, trying to find signals inside all the data that we collect, and we have a large amount of data there. Using developing machine learning methods, also known as artificial intelligence techniques, in order to extract out these very difficult and very small signals. Another project is looking for stealth supersymmetry, a very interesting new way of looking for an exotic phenomena which may or may not be there. Another project which I have, which is precision timing, the problem of distributing a clock.
So the timeline is run 3 of the LHC. Means we will be having a lot more data, so we'll be able to measure things a lot more precisely, and we'll have access to signatures that don't happen as often. And so there could be some surprises there where maybe a process that's been hiding sort of under the covers right now, we will have enough data to actually see it. So it's always a possibility. And what a lot of the new machine learning techniques that are coming out, we're becoming more clever every day and designing different analyses that can expand our reach. And so I would say, hard to say what would happen, but I'm still quite excited about the possibility of a discovery, maybe some new physics, or we measure a property of the Higgs boson that isn't as we expect, for example.
And I started my research in working on the Large Hadron Collider. But then when the dark matter searches started getting interesting, and it looked like maybe we'd find dark matter in an experiment that looks like a particle physics experiment, I got involved with the cryogenic dark matter search. And what we're doing now is we're building a larger and more sensitive detector and a complete experiment in a deeper mine so that we can get rid of the backgrounds which can affect our ability to see dark matter. And this new experiment is called Super CDMS. So we explore different kinds of detectors that might represent the generation after the Super CDMS. So actually I have a detector here. You can see it's about the size of a hockey puck, and it is solid germanium. We actually have both kinds, silicon and germanium. What happens is these are stacked in towers and put in a cryostat.
So I'm actually also involved in the LDMX experiment, which is a dark matter experiment. I'm not traditionally used to playing with dark matter. So I like to say the only thing we know about dark matter is that it's called dark matter. So we really don't know much else about it, and we're just looking in all sorts of places that we haven't looked before. So LDMX is going to use a high-power electron beam. It's going to be based at SLAC, which is in California. The nominal experiment design is to use this electron beam to search for dark matter being produced by electrons interacting with other materials.
We make measurements of the polarization of the cosmic microwave background. We make those measurements from balloon-borne experiments. And measurements of the polarization of the cosmic microwave background encode information about the physics of the Big Bang and encode information about the neutrino mass to separate the emission of the galaxy from the emission from the Big Bang. And so this is the unique niche of balloons, and for what we are proposing to do, that we will provide that extra leverage that is not available from the ground. Detecting those signals that we're looking for, people have said that's a Nobel Prize. But detecting them at high confidence is going to take some slogging through. What would you want to do other than work on those two big questions in physics?
So right now, the neutrino group as a whole, we have 3 faculty heavily involved in neutrino experiments. Myself, Marvin Mashak, and Greg Pawlowski.
I'm working on neutrinos, big neutrino experiment, the NOVA experiment. We built here in Minnesota. We built the detector. And it's taking data. And right now, I'm working mostly on an experiment called mu-to-E, which looks for a transition of a muon, which is basically just a heavy electron, to an electron with nothing else. And in order for that to happen, there has to be new physics. Right here at Minnesota, we're building the electron tracker, which determines the energy of the electron, which is sort of the bottom line of the experiment, to measure that energy of the electron very, very precisely.
We're involved in the DUNE experiment. So that's going to be based just one state over in South Dakota. It's going to be the world's largest and most sensitive neutrino detector. And we're going to discover all sorts of interesting things about neutrinos and how they change type as they travel. So you start out with what's called a muon-type neutrino, and sometime later, about half of them have turned into tau-type neutrinos. About 10% of them turn into electron-type neutrinos. And the real thing that DUNE is going to tell us is whether neutrinos and antineutrinos do that in the same way. Now, the reason that they're particularly interesting is that, in principle, neutrinos and antineutrinos don't have to do this at the same rate. So it might be 50% for neutrinos, but 45% for antineutrinos. And that, coupled with a few other things happening in the early universe, can actually explain why we have a universe that's made almost entirely of matter and not made of a 50% matter-antimatter mix. Something needs to be different between the two, and neutrinos might hold the key.
In the next 5, 7, 8 years, you can't do any other measurement other than what we want to do to determine the neutrino mass. Any other cosmological constraint requires the measurements that we're going to do. And what can be short of revolutionary if you determine the mass of a particle in physics?
If you join the group, not only will you learn some physics, but you'll also learn some real skills. For the CMS group, what we do, generally people come here, they spend 2 years or so taking their courses, in which case they're always based here. And then, depending a little bit upon the interest of the person, they can either go and spend a year, maybe 2 years over in Switzerland, working at CERN, the center of the universe for high-energy physics. There you would learn so much. There's certainly work to be done here for the construction of the project, be involved with a lot of the testing of the hardware, development of the hardware.
So if you were to join my group, you would work on a variety of different things. And so in our case, it would be mostly focused on electronics, where we're building a brand new calorimeter that's based on silicon and scintillator technologies. And we are in charge of designing and constructing and testing. The other part would be data analysis. That would be what you would write your PhD thesis on, for example. and there's a lot of options there. You don't need to worry about already having some prior knowledge about electronics or about supersymmetry or any of these kind of things. You will all learn as we go along.
Sometimes we do our research in this in the lab here. We have to operate the experiment, and so for the first year we'll be basically building it and commissioning it. But after that, students will be expected to travel up there for shifts. So you will operate the experiment for about a month, and then you'll come back. But you'll also be taking what we call off-site shifts. So you'll be here at the university looking at a large computer screen and actually controlling the cryostat and the helium dilution fridge and looking at the data. Everybody in the experiment does data analysis. Everyone's very excited to find out what it is that we've seen.
We believe that a graduate student should get sort of what you might call a well-rounded education, in that you should get experience analyzing data, but not just analyzing data, also building the equipment.
The lab is here in the 3rd floor. We build the instruments here and in collaboration with other collaborators at various places in the world. And we are planning to launch again in Antarctica and in New Zealand. You would be involved in a range of activities. You could certainly be involved with a lot of hands-on work, putting the instruments together. It involves a whole bunch of mechanical engineering, electrical engineering, a whole bunch of physics, cryogenics, millimeter wave instrumentation, vacuum. Launch opportunity would be about 4 or 5 years from now, which is perfect for graduate students to come in and work. And typically those are the time scales. We have a project, we build a project for, let's say, 5 years or so, and then we launch and we analyze the data.
So you could be sitting behind a desk at a computer in Minnesota, writing code that analyzes data, writing code that simulates experiments, and performing calculations. You could be in a lab. You could be building an experiment, you could be prototyping components, you could be doing research and development into these new detectors that we're going to need to build for Dune. You could be based off-site at Fermilab or at CERN, working on the experiments actually where they are, or even in South Dakota potentially. It's really, really flexible given what graduate student, what your interests are, where your skills lie. You can do all or just some parts.